Okay. I'll introduce the first question. The first question is maximize sum of array after K negations. Array A of integer is given. We must modify the array by negations. The negations means we choose array AI and replace it with negative AI. And then we repeated the negation K times and get the maximum size of the array. Let's look at the examples. The example 1, the A array has 4, 2, 3 elements, and the negation time total is K is 1. That means we have to negation 1 time to get the maximum array. Look at the 4, 2, 3, and we pick up the smallest element 2 and negate it, replace it with negative 2, and we got the maximum sum of the array. And the sum of the array now is 5. It comes from 4 plus negative 2 plus 3. And example 2, we have 4 elements here. And the K time is 3. That means we can negate 3 elements to get the maximum sum. We choose, first time we can choose the smallest one, negative 1, to place it with 1. That become 3102. And now the smallest element is 0, and we negate 0 to 0. That's it, also 3102. And the third time, the smallest element is also 0, and we got the same array 302. So the maximum sum is 6 now. And we can quickly look at the example 3 here. The K is 2. That means we have to negate some elements twice. Look at this array. The smallest one is negative 4. We just negate the negative 4 to 2, negative 3, negative 1, 5, and 4. And now the smallest element is negative 3. And we negate this element to get this array. And the sum of the array is 13. Yeah. Is that clear for this question? How to get the maximum sum and how to do the negations for K times? Yeah. My first thought is to sort the array and negate the first K element, but it's not true. When I explain the examples, and I noticed there is a constraint here. We can repeat this process K times in total, and this is an important constraint. We may choose the same index I multiple times. So look at the example 2. if I sort the array and negate the first three elements, I cannot get this array. That means each time I have to negate the smallest element, but not the first k smallest element in the array. Do you have any thought of the implementation?
Yeah, I have a sort implementation, but if everyone's fine with this implementation once you explain, then I can take up a sort implementation if you want.
Yeah, I just want to discuss how to approach this question.
So after you sort and you negate the k element, and what type of problem you see?
I see is the negation. The element I would like to negation is the smallest element of the array. It's not the first k element. Like example 2, the k is 3. After I sorted the array, it becomes -1, 0, 2, and 3. It doesn't mean I negate the first three elements. If I negate the first three elements, I can't get this array.
But you can actually negate the first element, that is a -1, and then again sort the array.
Yes.
You will always get something like a lowest element and keep on negating that. So the way you might do for the other data structure.
Yes.
I think that might also work, right? It's just a thought.
Yeah.
So my thinking, let's take the first example, only the positive.
Yeah.
And k, let's say k equal 3 right now. And how would we solve it?
If k is 3 now, so the first step is negate the 2 to become the 4, -2, and 3. And when the k is 2, the -2 is the smallest element. And we negate this to become the 4, 2, 3. Yeah, that's the possible maximum sum of the array. And the k is 3. We again negate the smallest element to become the 4 minus -2 and 3.
Okay. So if it's all positive, then it seems like we only negate the smallest number.
Yes.
Off and on, right?
Yeah. Because each step you have to negate some element. So if you negate the smallest one, and that means you will get the maximum sum of the array. Yeah.
I think if we have odd number of k, odd value for k, we can go for flipping the smallest element always. That would be one of the hard and fast rule, I think.
Yeah.
Let's say if k equal to 5, then again choose the smallest element in this and do it 5 times. That will maximize the sum of the array, because at last, again, at 5th iteration, that smallest element will be only negative. So the sum would be greatest in that case. I mean, largest.
Yes. So if it are positive, then we keep negate the smallest number. And if k is, let's see, if k is odd number, then we know that would be the negative, right? But if it's k even number, then we know it's gonna switch it back to positive.
Exactly. Yeah.
Yeah, but you don't know if all the elements in the array are all positive or negative or 0, like this array. Yeah.
Yeah, so
Just
I think that
negate one.
if we can treat them case by cases, like if it are positive, we treat it this way. If there's, you know, a zero in that, we treat in different way. And if it's negative, if there's a negative number in that, we treat, you know, different way. Maybe it's gonna work.
Yeah.
So,
Yeah.
yeah, I wanted to add a simple approach, like we could sort the array in ascending order first.
Yeah.
After sorting it, after that you convert all the negative elements to positive until no more flips are required or there are no more negatives. And if after that, if you find if there are an odd number of flips remaining, then flip the smallest element in that case.
Yeah. That means if after the sort you flip all the negative one. Yeah.
Negative elements to positive until no more flips are there.
If you're discussing the sorting approach, can I share my screen? I have solved it using that approach only.
Yeah,
Okay.
sure.
Yeah.
Okay. All right. Is my screen visible right now?
Yeah.
So what I have done is, like, I've sorted the array once. Okay.
Yeah.
And then what I did is I first counted the number of negatives, and I just checked if I have a zero in this array or not. I'll tell you why I did this. So how do we get a better sum is, like, if we are able to convert these negative numbers to a positive number, like that is when the sum increases when we do a negation, right? So
Exactly.
what our goal should be is to first convert all the possible negative numbers that we can to a positive number. So that's what we are doing. So let's say I have the count negatives, and till k is greater than 0, I negate all these negative numbers. So let's take an example that we can run through.
Exactly. Yeah.
So let's say this is the array. So after sorting, this would become -4, -3, -1, 2, and 5. So what we'll do is, since now k is 2 in this case, so we have two operations. So what we'll do is, first we'll negate the maximum negative number that we can do. So starting from the 0th index, where the maximum negative number will be there. So if we negate this, we can add, like, I first calculated the initial sum, which was of the array, right? Then if I negate the first element, then what will the sum update to? So the sum will update. So we'll have to take off, like, I initially subtracted -4 from the sum, and now I'm adding a 4 into the sum. So the sum will increase by 2 times the negation value of the negative number. Is that clear?
What is the significance of 2? I mean,
so that's what I'm telling you. So I first calculated the sum, the initial sum of the array. So I did 2 plus -3 -1, like in the sorted array. I did -4 plus -3 plus -1, 2, and 5. So I've already taken -4 into the consideration of the total sum.
No.
Now I am negating the -4. So earlier I subtracted -4 in the original sum. So now I have to add the originally subtracted -4, and now I'm adding the negated value of -4, that is 4. So I'm adding 4 2 times into the sum.
Yeah,
Because,
got it.
got it?
Yeah.
So, and then I'm just making this value positive in the array to mark that I have negated this value, right?
Yeah.
Then I increment I and I decrement k. That's a simple. Similarly, I do this for this part. So now my k is 0, and I don't have any operations left. So after this only, I'll know what the maximum sum is. Fine. But let's talk about the corner cases where we have k's left over. Right? Let's say k was, let's say, more than, let's say it was 5. Okay. So then I would have negated all possible negative numbers that I could have. Then let's say it was 6. Then I would be left with 3 operations. So what 3 operations mean is whenever there is an odd number of negations, I would change the sign. So I would have to give up a positive number from the sum, right? And converted it into a negative number. So I'll try to minimize that. Okay. So one thing is, like, if I have left over odd number of negations, but I have a 0 in the array, okay, I can simply keep negating the 0 the odd number of times that are remaining, and my sum will remain the same. So I don't need to do anything in terms of if I have a 0 in the array. But if I don't have a 0 in the array, what I'll have to do is I'll try to select the minimum number which is currently in my array, and I'll remove that from my total sum. So what I have done is, if the number of negations that are left after trying to convert the maximum number of negatives to a positive number, what I'll do is, let's say there is one, I'll tell you why there is a left bounded, just consider this for the one. So I take the last negated number which I did. So I was negating some numbers, like I was negating -4, then -3, then -1. So if I still have left negation operations, even after I have converted all the negatives, I'll consider the last negative number that I negated, right, which is pointed by the L pointer. Okay. In case of no negatives, it would be the 0th element, because that would be the smallest element of my array, right? And I'll negate it. So similarly, I'll just subtract it from my current sum. So what I'll do is I'll remove the value, the positive value that I have added in the sum, and I'll add the negated value to update the sum, which it would be currently now. All right. So this happens when there are, like, I have exhausted all the negative numbers in my array, and I still left with odd number of negations, or I don't have a 0 in the array. That is the case when I negate the last number back to the negative, and I'm done with it. But let's talk about this right pointer, which is an edge case for this problem. Is, let's say this was -2, and this started with 1. Okay. So in this case, what happens is I would have converted this -2 to 2. Okay, I have negated this -2, and I've added it to the sum. But now I still have, let's say I still have an odd number of negations left. Okay. But now I can't, if I negate this 2 back again using this left pointer approach, if I negate this 2 back again, I lose 4 from the total sum. Okay. But if I negate the first positive number, if it is smaller, so that's what I've checked. If the first positive number is smaller than the last negated number, then I have to negate the positive number. So I'll just negate this -1. I'll only lose 2 from the total sum instead of losing 4 if I negate the last sum. Is this edge case clear? Why we are doing this? So this is the simplest approach. You just need to sort the array once, and you don't need to go through all the case. In case of k is large, I earlier solved it with the heap approach, but it was kind of slower. And this was the approach that I found out to be the fastest one up till now. So you just need to sort the array once, and starting, you try to maximize the negations. So you try to maximize converting all negatives to the positive if k supports that. If k does not support that, it's well and fine, because you've already considered them in the initial sum, and you're changing the sum accordingly the number of negations you're able to do. But if you have exhausted all negations, then you just need to check this edge cases, that if you have a 0, these only I think 2 or 3 observations are in this thing that you need to take care of when you see this problem. Is like, if you have an odd number of negations, you need to change the sign of the number. If you have an even number of negations, you can simply ignore it and have the current maximum sum as your result. And if you have a 0, you can perform operations on it, and you can forget about if the k is odd or even or whatever. So these 3 are the key observations of this problem. If you get that, then I think it's pretty simple.
Yeah.
Any questions on this? If anyone wants to ask something, any doubts?
Why don't you keep track of the minimum, instead of doing the, operation on line number 29 or 30?
Which one? Line 29
and 30.
Okay.
Yeah, why don't you keep track of the minimum number?
For that, I'll need to either build how do I track the minimum? I need to create either a data structure, which is the
you can just keep track of the smallest positive number.
Min function, within min function you can pass the a of I or a of I minus 1.
So that's I is keeping track till where I have negated the number, right? So after that, I know it's going to be the minimum positive number, right? So I just need to, these 2 pointers are only, I need to check the least positive number and the last negated number, right? If the least positive number when is smaller than the negative number, then I will be losing more if I negate the last negative number, right, from the sum. In this example that I showed you. So let's say if it was even a higher value, let's say there was -5, 1, 5, and k was 3. Okay.
No.
So if I first I'll do one operation, which is negating the k, this -5 to 5. All right. I'm not modifying the order of my sorted array. So I just modified this to mark this as negated. And I added, my original sum was 1. Now it became 11. My original sum that I calculated was 1, and now it's 11. All right. So now if I negate this negative number back again, then I would be losing 10 from the original sum, right? The max sum.
Exactly.
But because my least positive number is less than the last negated number, I decide to do the remaining operations. If there is the remaining negation operations on this, so I'll just negate -1 here. Do this, and I'll just lose 1 from the original array, and my maximum sum would be 10. These are just pointers to the last negative. L is the pointer to the last negated number, and R is the pointer to the first positive number in case the array does not have zeros.
And if there are zeros?
So you can ignore it because you can perform the remaining negations on 0 and you can still have the maximum sum that you have calculated up till now.
Yes.
So, I mean, to make it simple implementation, I'm just thinking that while we are actually counting the negative number and negating those negative numbers, just keep the track of the smallest positive number, whether it's a 0 or what, and then in one shot, we know that what we have to do next after that. We don't need to do all these things. That's what I'm thinking. To make it simple though, I mean, your implementation is optimized in terms of performance.
Absolutely. We just need to check if we have exhausted all the negatives that we can negate, and if we still have an odd number of operations remaining and we don't have zeros, then only we need to check this condition, the least positive number and the last negative number negated. That's only thing we need to check if we have exhausted all the negatives. If we have not, then it's fine. We just negate the least negative number which is there.
What if, like, let's say we have a priority queue, but that priority queue only store the negative number, and at the same time we track the minimum of positive number, right?
Okay.
So if we have that priority queue, then we can process through that priority queue of only negative number, and then when we know when the priority queue is empty, right? And then at that time we already know what would be the minimum of the positive number.
That's another approach. Yeah.
So you're saying, let's say I put all my negative numbers, let's say -4, -3, and -1 in a priority queue. Okay. And I have, let's say, k equal to 2 in this case. All right. Or let's say k was, let's say I exhaust all the negative numbers. 4, let's say k was 4 here. So I first negate the -4. Okay. And what do I do after that? I take it out of the queue.
Yeah. You put the 4 into the priority queue again and pop up the minimum element from the queue. Yeah, always negate
that was the earlier approach that we discussed, right? So to keep all the elements in the priority queue. That's a simple. That's a very simple approach, but it's not like time optimized in this case.
This is space optimized.
Yeah, this is space optimized. The time complexity is similar for both of them, I guess. N log n only.
Yes. But it has the extra space. Yeah.
Yeah. This is a constant. Okay, if it's clear, then I guess you can. I just wanted to share the sorted approach, like how I did that.
Yeah, thank you.
Okay. Have any question about the first this question? If not, we'll move to the second question.
Yeah. So in this case, if we do the sort, the runtime complexity will be n log n.
Yes.
And the space complexity will be constant, right?
Yes.
Space will be order of n, I think.
No, I'm not using any extra space. So, and just using the original array only. I'm modifying it while sorting. So everything else is constant space.
Yeah, for the extra space, it's the better solution than the priority queue. Yeah. Could we move to the second question?
Yeah, sure.
Yeah, sure.
Who is
Okay.
the host for the second question? Maybe you?
Yeah, I'm the I was
Okay.
taking up the second and third one.
Okay. Yeah.
Okay. So can I share? Let me change it to let me change this to a whiteboard. Okay, yeah, is it visible?
Yeah,
So let me just give an overview of the problem. So we are given integers from 1 to 9. Okay, this is really hard to do this.
Or you can just type it.
Yeah.
Google Doc. Yeah, that it's okay.
Fine. I'll just explain this. So we're given integers 1 to 9 and we're given a number k. So we need to find if all the possible combination of k numbers that make up to a given sum of n. So let's take an example. It's saying given n equal to 7 and k equal to 3. We need to find all the possible combination of 3 numbers in 1 to 9 that give the sum to 7. All right.
Yeah.
So this, if you already see like a 2-pointer approach to this problem, this is kind of similar to that. So what we, yeah, three-sum problem. So what we do in that case is we fix one pointer here and then one pointer at the start and then one pointer at the end. And then we check what is the current sum. So the current sum is 9 plus 2, 11 and 1. So it's 12 right now. So what we do is it's greater than the current sum that we need. So we reduce the right pointer to 8. Okay. And then we check what's the current sum. It's still greater. It's 11 right now. So we move it further right. Then we move it 6. Then we move 5. It's still greater. So move it here. And here we find a sum that is matching. Okay. So we add it, we store it as a result. Then similarly, we can fix this now and then check here, right? So this way we would be ensured, like we go through all the valid subsets. Okay.
Yeah.
So you move this here and you start with here, and then you can see whether you're getting all the subsets or not. So this is kind of a 3-pointer approach. For 2 pointers, you just do this. So the basic problem, which is the core idea of that problem, was, so you fix a point here and then you check if k is equal to 2, if there is something which gives the sum 7. So for 1, it will give here 1 and 6. Then you can increment the pointer to 2, right?
Yeah.
And then you can find another subset here. Okay. You reset back the pointer back to 5 and then 3. So you can find a subset for this one as well if you want. So it would be 3 and 4. Okay.
Yeah.
And then after that, you won't find any subsets for this problem. It will cross every time. All right. So the main issue with this is k is an arbitrary number here. So k can be anything. Okay, so how do we go about and solve this problem when k is different? So we know how to solve it for a single pointer. Like if I'm just k is 1, we can just check if the digit is in 1 to 9, then we can achieve the sum. If not, we can't. In case of k equal to 2, we know how to solve it. Okay, so how do we go about solving an arbitrary number of k, adding on this idea that we explore these subsets and if they form a set or not? So does anyone have an approach, or should I discuss?
I think whenever we have these permutation problems, combination problems, we usually go for backtracking. Like
Yeah,
we'll
yeah,
take.
that's absolutely right.
So I was.
Would you like to elaborate on that?
No, just the thought. Like I need to think more. Then only I would be like it's like you take the first element one you took. You'll subtract it. You make some partial solution first. Like let's say initially the empty list is passed. Okay.
Yeah,
Now
yeah.
one you will add to the list. Now once you add one, you'll subtract one from there. What you say? The target, whatever the target value you have to get. Next time again we'll go through two and check it if we will have some corner cases, like if it is on adding the two, if it is exceeding the target, then in that case we need to track back. I mean we'll backtrack. Sorry, we'll backtrack and go to the next. Something like that. I'm not pretty sure about it. Like.
Okay, that was Sashank, right?
Yeah.
Yeah. The thought process is absolutely right. So what we'll do is we'll first select one in our path. Okay.
Yeah.
So let's say current selected array is 1. Okay.
Yeah.
So this is path 1. So I'll check whether the sum is still less. So I would be given an n equal to 7. So if I I'll check my current, I'll keep a track of current sum, what I've achieved in my current path, and a k. I'll keep track of k. So initially I'll have k as 0. Now because I have one element in my path, I'll have a cur k, like I'll store what my current k is in this path and my current sum. All right, these two things I need to keep track of. And my target I know is 7.
Yeah.
And my target k is
6. Oh,
4.
3.
Oh, sorry, 3.
3.
Yeah, so I have selected one in my path, one element in my path. So for all elements, I'll try to find a path which has the path length of the target path length and the sum as the target sum. So when I select 1, so it's kind of like fixing a pointer at 1. Then I recursively call for 2. Is there a path when selected 1 and selecting 2? Does there a path exist? So then I update this. Okay, this does not modify, I guess.
I think Google.
Let me just check if this modifies or not.
Use this paint part only. I think that will be simple.
Okay. So then I'll select 2, right? And then this is like setting a pointer here. And now my k would be updated to 2 here. Okay.
Exactly.
So my path length is 2. It's still less than the target path. And my sum is now 3, which is still less than the target sum, which I want. This would be 3 right now here. And my target sum is still greater than the current sum. So what I'll do is I'll try to select another pointer. So now I select 3. Okay. Now k is equal to 3. All right. So what happens is I have achieved the target path length. Okay. But if I add a further element in this path, then this constraint won't be satisfied, that the path length should be 3. Okay.
Exactly. Yeah.
And this current sum is not equal to the target sum. So what I'll say is that this is not a valid path. Okay. When one of these constraints violated, that my target sum becomes greater. Okay. So
Yeah.
when are the conditions violated? When my current sum becomes greater than the target sum, or the current path length becomes greater than the target path length. Okay. So I'll return. So while selecting 1 and 2, then selecting 3 was not a valid point. Okay.
Exactly.
Not a valid point. So I'll add, then
4.
I'll go to the next valid choice that I have is 4. So is 4 a valid path? I'll see, yes, 4 is a valid path for this approach because the target length is 3. Okay. And the current sum is 7, which I wanted. So I'll add these 3 elements in my resultant array and I'll move on. Okay. I've returned because this, I don't need to explore any further on this path. Okay. Then I'll check for 5 because the target sum is greater. I can simply break out. Okay. I don't need to explore any further. Okay. Then we have backtracked back to fixing when we fixed the second pointer. Now I know I have explored all the paths with fixing 2 as the pointer. Okay. Now I'll move this here and then I'll start exploring other paths with 1 and 3 as the fixed elements, and then starting from 4 I'll check whether this is a valid path or not. Okay. Then here, then here, then here. So whenever the sum is greater than this, I can simply move out. Right. We can do this for, let's say, any number of k. So we'll just have the recursion call going greater and greater. So in case of 2, let's say, which is the easiest example. So how will you do is, for you'll just run a loop. So I'll just show the code for it. Before I show you the implementation, is there anything that you want to ask about this approach?
Yeah, I get that approach. I have a question. So the value of the k is always 3, or like it can be changed to any other?
So we can have the values of k anything. So it could be 1, it could be 2, it could be 3, it could be 4. So the main constraint in this problem is we are only allowed to use digits from 1 to 9. Okay. And we are allowed to use each digit only once. Okay.
So if k is 9, so in that case, how it will differ?
So if k is 9, there is only one possible combination of all k elements. Okay. So that is 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 should be equal to the target sum. Yeah. If it's so not,
that will be easy. Yeah. Okay.
Yeah. If it's not, then we can't have an array.
I think those are corner cases. Like.
Yeah. Those are the corner cases. Like if in case of 1, k is 1, right? Then you just need to check if the number is less than 9 or not. Then
if the list itself is empty, or the length of a list is greater than k, in that case also I think, let's say the length of the list is 10 and k is 11, then in that case that's also like one of the corner case we can add. False only in that case we have to return.
Okay, so the list won't be empty because the question says that you're given numbers only from 1 to 9 and you can use them only once. Okay, so you have this fixed number of digits, like these 10 digits or 9 digits that you have, and you need to make the target sum of k subset of subset k. So you need to have like k elements from these 1 to 9 digits to make up the target sum. So I'll stop sharing this whiteboard.
Just one quick question. So can we use a dynamic programming tool here to avoid the repetitive?
So you can easily, like in backtracking, you can easily prune these paths. So let's say I have selected 1 and 2, and here I have 3. Okay, so after this 4, right? Let's say your target sum on 5, you've increased this. Okay, so you don't need to explore 6, 7, 8, 9 because you know you're not going to find a result given earlier idea of 2-pointer approach, if you know. So you know you're not going to find a target sum when you increase this pointer further ahead. Okay,
Okay.
so you
But
can prune the following paths here. So once I found 1, 2, and 5, while fixing this, I know that my targets like current sum is going to be greater than the target sum. So I'll return from here, and then when I fix this 1 and 3, right? And then I would fix 4. I'll find this. I'll see that this is okay. This is equal to 7. But after this, I'll know that all the further paths that I want to explore on this path are not useful for me because I know the current sum would be greater than
okay.
required. So you just need to prune those paths. So yes, you save yourself extra computations that you want to do.
Okay.
Yeah,
Thank you.
I have a question. What's the complexity for the 2-pointer approach? Is it different from the backtracking? Backtracking is 2 to the power of n time complexity for the combination problem. What's the complexity for the 2-pointer approach?
Okay, so you can't really do a 2-pointer approach here, but in the 2-pointer approach, let's say you just have 2 pointers here. So this is a linear complexity. Okay, you'll find all the possible subsets here. Okay, like the valid ones which make up the target sum in a linear time. Okay,
Only if the array is sorted, then only. Otherwise.
yeah. So you know these digits are sorted, right? 1, 2,
Yeah,
3, 4,
exactly.
5, 6, 7, 8, 9. So this 2-pointer approach only works in this case only. But here the main challenge is the k value is arbitrary. Okay, so it could be anything from 1 to 9. So in that case, what we need to do is we need to explore all the possible subsets of length k, right? So
Yes.
let's say, so that would be a challenge, right? So you need to explore all possible subsets of k length and check whether they form the target sum or not, right?
To my earlier question, so if you have the dynamic programming implementation, like we still have here some repetitive things, like right here,
Okay.
like if n is equal to like 3, and if k is equal or n is a target, right? If n is equal to 12 and
Okay.
k is equal to 3, so let's say if you start with 1, 4 and 5, that combination is still like less than 12, so you may continue after 5, right? 1, 4 and 5. So 1 plus 4 is 5, and when you are at 5, the current sum is like 5 when you reach 5, and even if you include 5, you will not get a target, right?
Yeah.
So,
Okay.
and
So
when you have 2 and 3, the sum is 2, 3, 5. The current sum when you take 2 and 3 is like 5, but still you cannot have the sum. And even if you,
how do you know that this does not form a valid sum if you've not explored it?
because at 5, I know what is the current sum, and I know what is the index at 5, like at
Okay.
5 comma 5, whenever I reach 5 with the current sum as 5, I know like I cannot get a target when I do first computation.
Okay.
So when I have like 1, 4 combination at 5, I include 5, so which will be total 10, and I go to 6. When I go to 6, like I'll not reach a sum because it's greater than 12. So I return back saying like false or some pointer, and at 5, while returning back, I'll update saying like at this 5 with the current sum, I cannot I cannot reach a target. So whenever I get a one more combination, say like 1, 4 at 5, like I can say like okay, this computation is already calculated, right? Because 1 plus 4 is like 5.
Okay.
And with a current sum of 5 and I'm at 5, so I already know I already calculated that computation earlier and I can return it back.
Yeah, you can do that absolutely, and just you'll have to like modify it for like number of pointers that are there. So let's say if k was 4, then you'll need to check if I'm already seen these many values, can I still get this value or not?
Yeah.
I think yeah, that's fine. So I guess if there are any other questions regarding the backtracking approach.
So the time complexity here will be constant, right? Because numbers are fixed from 1 to 9.
Yeah. Well, you can say that.
Okay.
The like selecting 4 from 9 digits is like the number of, you need to select k elements from these 9 digits. So and you need to explore all these possible combinations, right? So
Yeah.
that's the complexity of it. So would you like to see the implementation of this?
Yeah, sure.
Okay, fine. Just share this text. Okay, is this visible?
Yeah.
So I just create a resultant array over here, and you just have n equal to 0 or k equal to 0. You just return an empty list because that's the base case. Okay, so if the target sum is 0, you know the target sum has to be greater than 1 because you are using digits 1 to 9. And if k is 0, you can't have any selections of the path. So this is a recursive function which says find matching. So what the parameters of the functions are, it's the current value that you are currently exploring, the current sum, the target length of the path, the target sum, and the path itself. And I am also passing the result array list so that I can simply add my valid matches over here and then move on. So the base cases are here. If the current sum is greater than the target sum, this is not a valid path. So I just need to move out of it. And if current, like the digit from exploring from 1, 2, 3, 4, it becomes greater or equal to 10, then this is not a valid path. So when k is equal to 0, that is, I am subtracting 1 from k each time I am going down the path. So when k is 0 in this case and the sum is equal to the target sum, then I have found a match. This path is a valid match for this target sum. All right. And if it's not, I'm just returning like this is not a valid path from here. So what I do is when I first go is I'm assuming that I fixed the pointer on this current, and then I'm adding one pointer for each number greater than, so let's say it was, okay, let me check.
Hello, Raunak, one thing here.
Okay.
When you are saying the current CURR, okay, and then you are iterating this for loop, okay, from 0 to 9, right? So we don't need 0 here, right? Because we only have the digits from 1 to 9.
Yeah.
So you could have done this like find matching 1 and then just here instead of adding current plus 1, you could have just made it current. I just observation, yeah. That's okay. Continue.
Yeah. We could have done that also. Yeah, I think following some thought process, and then I
got some different thing. Okay, no problem.
Yeah. So what this was like, I was trying to fix the pointer to the next element in the digits. So that's why it's current plus 1, and then I'm adding this to the path, like the current which I've selected, and then I'm recursively calling for setting the current as, so Eventually, yeah, what you said is right. I'm eventually calling this from 1 and then adding 1 into the digit and then subtracting it from the path. Okay. And then once I've explored all the possible paths from 1 while fixing 1. So first I'll fix 1. So it's kind of like a depth first approach. I'll fix 1, then I'll fix 2. Okay. Let's say for k is equal to 3. And then I'll fix 3 here. Each time I recursively call for cur plus 1. Okay. So each time I recursively call for 1, I call for 2. Then for 2, I call for 3. So when k is equal to 3, if this is matching, I'll return. So the call will return to this call where I had set 2 as the current, and then it would explore 4, then 5, then 6, then 7, then 8, then finally 9, right? Then this would go back here and we'll fix 2 and 3. Okay, so does that make sense?
Yeah. So the path remove is the backtracking in this case, right?
Yeah. So once I've explored the path, so I've added, like in my current path, I'm adding the current value, right? With that current value, once I've explored all the paths, I am removing it from the current path, and then the loop iterates further, and then it adds the next element to the path. Okay.
Yep. Perfect.
Yeah. So are there any questions about the implementation or the approach?
I have a question about so the path dot remove actually removes the one single element that is currently on being returned from the
Yes.
stack, right?
So yeah, so we're recursively adding this. Let's say initially it was an empty array that I passed to the current path. Okay.
Yeah.
So after that, I add 1 to the current path, right?
Okay.
I'll explore 1, 2, right? Let's 1, 2, 3, right? After this, like when k is equal to 3, right? When k becomes 3, that is k, in my case, it would go to down to 0, right? I'm returning from here. So I know I have explored, I've added all the possible elements that I could have added in the path, right?
Yeah.
And now I need to check for a next path. So then the loop will iterate further, and then it would add 4 to the path and then check whether it's a valid path or not. So that's why I just need to remove the last element from the path. So when I've explored, let's say I've explored till 9, all right, I remove this 9, and then the call comes back when I fixed 2, right? So I know I have explored all the paths when I added 2 into the path. Okay. So now I can remove 2 from this, and the loop will iterate further, and then I can say I now have to explore all the paths that are starting with 1 and 3. Then similarly it would go down recursively, and then it would add 4, 5, 6.
Yeah. I've tried different I've tried backtracking but with, let's say, strings, and I remember that I didn't need to actually remove any character, because I guess the string is creating a new string every time, correct? Whenever you go back. But in this case, if it's a list, then we gotta remove the last element to backtrack.
Yeah.
Got it. Okay. Thank you.
Okay. So I guess that's it for this question, I guess.
Yeah, that's fine.
Yeah.
Okay, so can we move to the next one?
Sure.
Okay, so this is a simple one, I guess. So it says you're given an m cross n matrix, and what you need to do is, if an element is 0 in that matrix, you need to set its entire row and column to 0. Okay, and the only constraint that they say is, they say do it in place. Okay, so this is, let me see if I can annotate. Okay, so okay, So this is the 0 here. So we need to do the whole row and the whole column of this matrix to be 0, which is the given output over here. So because of this 0, its entire row and entire column was marked as 0. So does anybody know how to solve this? Would anybody like to explain?
I think we can record whether the first row or first column contains 0.
Okay, yeah.
And
so what a basic approach would be, so I'll just first tell you what the naive approach would be, is like you create another array, okay, and you copy all these elements here, right? And whenever, let's say you're iterating the original array and you see a 0, you make all the whole row of the copied array as 0 and the whole column of this as 0. So the main problem with this approach is it takes a lot of space, and why we need a copied array is if you modify the original array, right? Let's say you were iterating 1 1 1, you didn't find a 0, then you got 1, then you got 0. So now that you have seen a 0, if you modify your current array is this, right? Then you go here, right? You go in this element 1, then you again see a 0 which was not present in the original array. Then you don't have any option of saying like, okay, then I'll mark this as 0, this as 0, so your output is wrong then. Okay, so if you follow this approach and do it in place over here, so that's the main problem that you're going to face, is like you're going to change the result. Is that clear why we need a copied array? And then when we find a 0, we mark the column and the row of the copied array as 0.
No.
Okay, so a better approach would be, because this takes m into n space, so a better approach would be to store all the indexes where there is a 0, right? You do basically a 2-pass approach. So what you do is whenever you see a 0, you mark it. So let's say you saw a 0 at 1 comma 1, right? And you store it somewhere. So you know there is only a 0 at 1 comma 1 index. And then in the second pass, you iterate over this array of indexes where there are zeros, right? And you make the whole row and column as 0. So the space complexity of this would be m plus n, given what the number of zeros are. Okay, so there are m columns and n rows. Oh, sorry, m rows and n columns. So that would be the space complexity of this approach. Okay, these are the two naive approaches, so which they already discuss here. Here over a straightforward approach is solution using an m into n space, which is probably a bad idea. And a simple improvement uses O of m plus n space, which is like storing all the indexes where you see a 0. So in this case, you'd store like 0, 0 and 0, 3. So, and then in the second pass, you'll take out first, you'll get 0, 0, and you'll make the whole row and column as 0, right? And then you know the next 0, which was present in the original array, was 0, 3. So you will similarly make the 0th row again 0 and the third column as 0. So that's the better approach of storing the indexes of 0, and then in the second pass, converting all those indexes, their rows and columns, to 0. Any doubts on these questions? Well, these approaches, any doubts on these two approaches?
No.
Okay, so yeah,
Raunik, quick question. So when you find a 0, you store the corresponding index into the same array.
Not the same array, you need extra space. So here you are copying the whole array, right? So you are making a copy of this whole array, and then whenever you found a 0, you made the copied array's whole row and whole column 0. And here you need not worry about getting an extra 0 because you're only iterating the original array and modifying the copied array.
Oh yeah, I understand that. With extra space, we can do that. But in case of in-space solution, right? So
so I'm coming to the in-space solution.
For the in-space one, like, when you do a first pass of like m into n, whenever we find a 0, we can just, okay, we need some, okay.
I think I am seeing the solution. I think whenever you find a 0, he's marking with -1, I think.
Your flag, you can use some like...
Yeah, so you can keep a flag number, which you say that I need to modify this number. All right. So that will prevent any extra zeros. So if I directly mark the whole row and column 0, so what would be there is I would further be iterating in that array, and then I'll see another 0, which was not originally there. But in this case, I'll see a flag variable, which is, let's say, a negative. Here I'm taking integer dot min value, so it would be negative something. Okay. So I'll see, okay, this value has been modified, so I don't want to consider this. Okay, I only want to consider when the element is 0.
So we can also do this, right? Like when the first pass, whenever you find 0 anywhere, just update the first row and the first column value to 0. And in the second pass, you can use that value to update rest all the row and column.
But
like in the first
in
the first example, like, if we find like, 1, 1 is 0, right? So whenever I find a 0, I update 1, 0 and 0, 1 to 0, 0.
Yeah, but
because in the next pass, I'll just use the first row and first column to see if there are any zeros and update respect to column and rows to 0.
So,
and for example, if
you update only this part, you're saying?
Yeah, I'll just update the first row, second column with the 0 in the first part. I mean 1, 0 and 0, 1. So after, like, if I find a 0, so my output of after, like, first two for loops would be 1, 0, 1, 0, 0, 1, 1, 1, 1.
I think if you write it as a marker, that would be more clear in the coordinates countries.
Yeah, can you write
1, 0, 1?
Yeah, 1, 0, 1.
1, 0,
0, 0, 0, 1. No, 0, 0, 1.
Okay, 0, 0, 1. All right.
1, 1, 1.
0, 0, 1. That's correct.
So, so this would be my first for loop. So in the first for loop, I'll identify what are the different zeros I have, and I update the respective first row and the first column to zeros. And in the second for loops, I can just use the first rows, whatever the 0, I'll update respect to all the columns and rows. Is that would be in place?
So now, once you make this as your array, right now, you already have a new 0 here. New 0
yeah,
here.
so in the next time for loop, I don't check any inner zeros. I check like what are the zeros which I have in my first row and a first column.
So you're just going to check these indexes over here.
Yeah, the first row. Yeah, first row. Yeah, those, and update respect to columns and rows.
Yeah, but in that case, for example, too, if you see, you have zeros at the 0, 0 position, right? So in the first row, you have a 0.
Yeah, so that doesn't matter, right? I mean, anyways, it's a 0. So
So when you're updating the row, the last 0 will go away, right?
Anyhow,
so you won't be able to come to know for that column that you have a 0 there.
So it's already a 0, so I don't need to check that, right?
But you have to, at the last column, you have to make it 0.
Yes.
So what about this input array? So what you'll do is first you'll see a 0 over here.
Yeah.
You'll mark this as 0.
Yeah.
You'll mark this as 0. Okay.
No, I don't need to check the first row, first column, right? Because I just need to check the inner.
You don't need to check this?
Yeah, I mean, the first row, first column, I don't need to check for zeros because
let me get this once what you're trying to explain. So when you saw a zero here.
Yeah, I always start my first for loop with the I is equal to 1, j is equal to 1.
Oh, diagonally is going, it seems.
Not diagonally. Like I'll start like, I don't start from first row, first column, but I start from, I mean like my first for loop won't be like I is equal to 0, j is equal to 0. So I loop through from I is equal to 1 to n, m, or j is equal to 1 to n.
Okay.
Because that way, like, I don't.
So what would be your resultant array after the first pass in this input case?
So that would be like, 1 1 0.
Okay.
Oh, sorry, 1 0 0. 1 0 0.
1 0 0. All right.
And 0 0 1.
0 0 1.
And 1 1 1.
1 1 1.
Yeah.
And what elements would you be considering now?
Only the first row, first column, like, I'll consider in the second for loops.
This first row, first column.
Yeah, because see, now the first row, row has a 0 in the first, first column and this, second column and the third column. So I'll update all the respective column values to 0.
So you'll update this as 0. You'll
Yeah.
update this as 0.
Yes.
Okay.
And that as 0.
Which one?
The first row, first 0. Yeah, 0 0.
How,
yeah, that's the index.
How do you know you need to update this?
Because there's already a 0 in that row, right? I mean, whenever there is 0, after my first for loop, in the second for loop, whenever I have a 0 in the first row, I update all the respective rows and columns to 0.
So here you already had a 0 in the first row. So why didn't you update this element?
That is taken care. That is taken care in the second for loop, not in the first for loop.
But what was the significance of doing only those two zeros? Like, what was the relevance of that? 0 above you did 0 and 0 left you did 0.
Yeah, I didn't quite understand the approach. Like how are you keeping track of in the second pass? And then it's like you're going to lose state if you update in the first pass, okay, and you do it in place. You're going to lose state of which zeros were in the original array and which zeros you have modified. That's the challenge in this question, I guess.
Maybe it might be working for this particular example.
This will work actually the way he's saying, because he wants to actually store the same information in the first column and the first row.
Yeah, that's
But
true.
you have to only take some corner cases. If you take care of that, that should work.
Yeah, because when I'm trying to identify zeros inside my array, I'm not updating. I'm not considering the first row, first column. So I always start with like, it's like, sorry to confuse. I always start with the first row and a first column. I mean, which in the sense like 1, 1 indices, not 0 0.
Yeah.
Okay.
Yeah, there are many ways to do it. Yeah, this is also one way to do.
Yeah.
So you'll keep track of which all positions in the first for loop you have made to 0, right?
Yes.
I mean,
let's take this example for him to explain. I guess that would help everyone better. Okay. So let's say you'll iterate in the first pass. You'll see the first element 0. So what you'll do?
Sorry, my first for loop doesn't start from
okay, so you
from
start
4
from
it
here.
starts. Yeah.
Okay, so 4 5 1 3. So this is how you go.
4 5 2 3 1 5.
Okay, 4 5 2
3
and
1
then you
5.
go 3 1 5.
Yeah. So I don't have any zeros, so I don't update anything. Okay. And I go to the second for loop. And now I check like what are these zeros available in my first row.
Okay.
Then I update respective columns and rows to all zeros. Like.
So you'll do this.
Yeah.
Okay.
Right.
And then you'll mark these zeros.
Yes.
All right. So, but now that you have marked this as 0 and you're iterating in the first row only. So how do you know that this 0 came as an updated 0 or it was already there?
Yeah, so in that case, there will be a corner case, right? You can actually use the first 0, 0 location to represent the 0th row to be 0. And you can use another variable outside saying if the first column is going to be 0, if that is true. So you have to mark that first when you're actually doing passing through all this. First you store those two informations, then you can take care of that too. That's a corner case to be handled.
Then wouldn't he have to store for all these columns, all these first columns, I guess?
Yeah, so what you can do, you can say the 0, 0 location, if there is a 0, I'm just going to only make the first row 0, and they take another flag outside saying, okay, if my column is 0. So first you can say, when you come here, you have a 0. So you can set that flag also for the column to be 0 as some variable outside.
Okay.
Yeah, and then you can say, you can check that variable. So, I have to even implement this column to be 0. So you can handle that. Yeah.
So you
one
store
separate variable here. So either you can have two variables saying first column to be 0 or the first row to be 0. You can have two variables, or you can use this location itself saying, okay, if there is a 0 here, I'm just going to say that my first row has to be 0.
Okay.
Yeah, it can be implemented that way, but yeah. So your way is also a very different way.
Okay, then he'll need, I guess, for how wouldn't he need for each of these elements, like whether
no. So the last 0, he will say this is only for the column 0, right? So when he's going through this, he says he is not going to look at these two, first row and the first column, means the 0th row and the 0th column. They are only the informations.
I guess he's checking all the elements in the first row,
right? Yeah.
The second pass, right?
Absolutely, that has to be done.
Yeah. So first he finds a 0 over here, okay, and he marks it somewhere that this is only for, I guess, column.
Yeah, that's a corner case. The row or column, yeah.
Yeah. So he marks it as a column 1, okay, and he does not update anything.
Right.
And
then he goes for the second one.
Yeah, let's say if it was also a 0, then he has to mark this as also column 0, right?
Yeah, I think that's a case I think we need to handle.
Yeah, so that would be right. So that's same as using like n space over here, right? The number of columns you're using. That's what I was trying to explain. So once you like update this, you lose track. So if you're going to store it as a flag in a temporary variable, you'll have to do it for like all the elements that you're checking.
No, you don't have to do. Maybe I can share this solution. That solution is also available.
Yeah, sure.
In our
yeah,
solution,
maybe. Yes, I
in the Slack we can. But that's possible. Very much possible. I can share this on the Slack. No problem.
Yeah. I guess that would help.
We should go through your solution. That looks very interesting. If you can quickly do that, you did something that update, right?
Yeah, if anyone else also has understood this approach, like if they come up with the solution and share it on Slack, that would be very helpful. Like, sure. What I did was like I just updated, like I marked each element as modified, right? So whenever I see a 0, I am updating this whole row as modified. So let's say this was a number as a flag, this as a number. Okay, so I know I don't have to consider these ones. Okay, then whenever I see a 0, I modify these elements. Okay, and in the second pass, I know that all the modified elements have to be converted to 0, right? So in the second, into the whole matrix and check if they are updated, then I'm updating the matrix to 0, right? And when I'm marking these elements as updated is when they are not 0, if there's something else other than 0.
Okay.
So I don't lose the original zeros in my array. Okay.
So you store the 0 information as is.
Yeah, so I don't lose the information of original zeros, and I'm able to mark what the elements would be 0 in the next pass. One problem that I faced is like in case of interview, I guess you'll need to ask what the input data is, because when I took integer.min value as the updated flag variable, so when I did that, I was getting an error. So I was like confused how to solve this one. So this has an input test case which has this element. So but if you take something else minus 1000,
can you try integer minus integer dot max value?
so you can do any else number and it would pass. So you could do anything else and it was passing. Only in case of I just wanted to share this what I faced.
No. Can you actually change it to minus integer dot max value instead of min value for the updated? Let's see if that works.
But that would overflow?
Overflow, I guess. That would overflow.
I'm not sure,
Let's see.
Yeah, I think it should work whatever the value, because it becomes a random value.
Okay.
But yeah, so anything other than integer or min value was working. Okay, so it was by mistake.
There's no integer, I guess. That's. I mean, the max value is kind of, if you negate it, is gonna be less than the smallest one.
Yeah, so that was a edge case in the test case. So you'll need to ask the interviewer like what is the values that are allowed, and that you have a value to have an updated flag. But if you don't have an updated flag, I guess, let's say he said all integers could be the value of this description. So in this problem, if you had every integer as an element of this matrix, then this approach won't work. And I guess what the approach we were earlier discussing, like if somebody can share that solution, I guess that would be great.
Sure.
So because you'll run into the same problem, is like when you modify this to this flag value, you won't know whether it was originally the flag value or you have updated it. So the main problem that is with it doing in place this question.
Yeah.
Okay.
No problem.
So what's the complexity of this solution?
So you're iterating the whole matrix. So it's m into n, right? But what the benefit is, you're using constant space. So you're just using the original matrix, you're just modifying the original array and then using it as a second pass to update those values. In the earlier approaches, which were brute force kind of thing, so those were only space inefficient. So you were earlier copying the whole matrix as a copy matrix and updating there. The second approach was where you store the indexes of 0 in an array, like as a pair, and then iterate over those pairs and then mark the original matrix element as 0. Okay.
Yeah, it's space efficiency. Yeah, but not the time efficient.
Yeah, because you need to iterate over all elements to check whether they're 0 or not.
I just would like to mention I use C++ and set the flag to the integer max or minimum. It doesn't work. Yeah, because the test case, it has the integer max and minimum in that matrix.
Yeah. That's the edge case, right? So, but if you pick any other flag, which is like some random value like this, it would work.
Yeah. It depends on the test case. If the test case had the minus 1,000, it's happy the flag.
Yeah, I think it would depend in the interview where you need to ask like what the value set is, like what are the values allowed in the elements. Here the constraints are not that specific. So then you can know actually that whether you can set a flag or not. Do you have an integer empty which can be marked as a flag?
Thank you.
Thank you.
Okay.
Yep,
So I guess I'll stop sharing.
You have to stop recording now because you are the host.
Okay.
Yeah, you just stop recording first.
Okay, let me stop recording.